What's up, everybody? Welcome to the fifth lecture of trig. Today we're going to be talking about graphs of sine and cosine. So to start off with, I thought I'd draw both the graphs unlabeled and see if we could use the unit circle to figure out which graph belonged to which function. Before we do that, though, there's some things we need to know about what these graphs are. In particular, we need to know that in these two graphs, the x-axis represents theta. It's the angle. It's our input, right? And the y-axis, well, it's just going to represent whatever our output is for a given angle. So whatever the value of our function is at that angle. All right. Having said that, if we look at our unit circle, we know that the x position can be written in terms of cosine, and the y position can be written in terms of sine. Having said that, if we're at an angle 0, we know cosine is 1, and we know sine is 0, right? Because we are 1 unit to the right of the origin and 0 units up or down. So it must be that we're at 1, 0. Okay? Well, if that's the case, let's go ahead and write that point down. 1, 0 at theta equals 0. Well, if that's the case, we can already identify which one of these graphs belongs to which one of these functions. Like I said before, the x-axis represents our angle. So if at theta equals 0, cosine is equal to 1, this first graph must be cosine. Let's write that down. Which of course means the second graph is sine. All right. So we've already identified which graph belongs to which. Can we start identifying now points inside of the graphs? That's another question we might ask, right? Well, as I increase the angle, looking back at our unit circle now, if I increase the angle and I get to 90 degrees, or pi over 2 radians, well, that gives me cosine of 0 and sine of 1. So let's mark that down. Cosine 0, sine 1 at theta in radians equal to pi over 2. Well, we know that this is our cosine, we already decided. At what point do we reach 0 first? Well, moving through, it's got to be where it goes through the x-axis, right? So here, must be the point 0, pi over 2. My mistake, pi over 2, 0 is what I meant to say. Sorry about that, guys. Pi over 2, 0. There's a thing back there. Okay. So if this is pi over 2, 0, and we know that in our other graph, we want to find where sine is equal to 1. That must be here. Pi over 2, comma 1. We might start noticing some things already. In both cases, it looks like the maximum point might be 1. the maximum height. And that's in fact true. And we might have already guessed at that, right? Because we know cosine and sine represent the height or the distance away we are from the origin, right? So cosine will only ever move between 1 and -1. Sine will only ever move between -1 and 1. So we might have already guessed that both of them are going to reach a maximum height of 1. Okay? Moving on through now, we were at pi over 2 radians. Now let's go to pi radians. Here, we're at the point -1, 0. And our angle in radians is equal to pi. All right? So moving on through, we find that at -1, we're right here. This is the point pi, comma, -1. And our sine value is going to be 0. So looking at our graph over here, moving on through, we see that it's our our x-intercept. Pi, comma, 0. Now, moving another pi over 2 radians, we get to this bottom point here, which is going to be 0, comma, -1 at 3 pi over 2 radians. So, looking over here, chugging along, we find that we move back through the x-axis right there. So that must be the point 3 pi over 2, comma, 0. And now, over here, must be this point, right? -1, 3 pi over 2. And of course, if we go another pi over 2 radians, we end up right back where we started. So at 2 pi, our cosine will be 1 and our sine will be 0. Well, that's going to happen right about here. 2 pi, comma, 1. And that's going to happen right about here. Two pi, comma, 0. All right, so we have some points of interest now, right? But we might also notice something else about this. In one of our previous lectures, I had talked about how cosine and sine are both 2 pi periodic. Talked about the periodicity of the functions. And I explained that it arises because, well, we're moving in a circle. After so many angles, we're going to end up right back where we started, right? Well, that shows up in our functions as well. Notice here, we were at the point 0, comma, 1. And if we moved along our x-axis by 2 pi radians, chugging along, we end up at the same height again. So here, we can think about it as returning back to the same point. In our graph, it translates as ending up back at the same height. But there's a catch. Notice here, cosine goes through 0, and here, cosine goes through 0. But they're not 2 pi apart. That's because there are multiple points that we're going to go through, multiple heights, I should say, or lengths. In the case of cosine, we're moving back and forth, right? So we're going to go through multiple points multiple times. In fact, we can see here, we're going to go past every point twice, except for the points on our very far ends of the circle. Same thing with sine. We can see that we're going to pass through 0 once, twice. But we started at 0, so it's really going to pass through the origin, through the x-axis 3 times. And we can see that show up here. So just some things to be aware of, right? Some relationships between the unit circle and the graphs of our functions. Having said that, let's move on. For this first example, I want you all to consider this graph. This is the graph sine of x is equal to y. Same exact graph we looked at, just extended a little bit further. Now, I want you all to consider while you're looking at this graph, what the graph of 2 times sine x might look like. Let me give you all a second to think about this. So assuming you just paused it, because I'm not actually going to give you a second, I'm just going to keep going. Assuming you paused it and have decided to return back to the lecture now, let's look at this graph here for a second and see if we might be able to use it to inform us on how to draw the graph for this. All right, so in this graph up here, what we've got is we've got our sine function. It's bounded between 1 and -1. And we've got a couple points of x marked that might be of interest to us. Take note of them because I'm about to erase them. All right, so what we're wanting to do is we're wanting to multiply this graph by 2. That's the same as stretching it in the y direction. So what it'll look like is pretty much the same graph, just stretched, right? Okay, so if that's the case, we can expect it to look something like this. Everywhere that it touches 1, it'll now touch 2. Everywhere that it touched -1, it'll now touch -2. So we can use these max and minimum points as a sort of reference. And everywhere it goes through 0, we also know that 2 times sine x is going to have to go through 0, because 2 times 0 is still 0, right? So yeah, it'll go through 0 at all the same points. Otherwise, it's going to look like I said, the exact same graph, just stretched. So now that we've got these guide points drawn up here, let's try to fill them in. So it'll look kind of like that, right? Drawing it over here, what we've got is a graph that looks something like this. Try to get this level. There we go. Close enough. So this is -2, and this is the line. My mistake. I should say this purple line is the line y equal -2, and this top purple line is the line y equal to 2. And we can see, like I said, it looks like the exact same function, just stretched now. That's all there is to it, really. Okay, all there is to what? What did we just do? Like, what just happened here? Well, what we just did was changed the amplitude of sine. We just drew the graph and all this A here is doing is changing the amplitude. It changes how high and low our function gets. Cool. Let's keep going. So another way to see what we just did, to illustrate what we just did, we know that sine of x is, quote, bounded by -1 and 1. It's bounded above and below. Cosine x is also bounded below by -1 and above by 1. So if we were to multiply all of this by a, or all of this by a, we could expect to get -a is less than or equal to a times sine of x less than or equal to a, or if we multiply all of this by a, we can expect to get -a is less than or equal to a times cosine x less than or equal to a. Wait, what does this mean, right? All this means is no matter what you multiply your sine or your cosine by, you're just stretching it. Where you would have been -1, you're now going to be at -a. Where you would have been at a, or I mean at 1, you're now at a. Your zeros stay the same. So where you cross that x-axis, those points stay there. But every other point gets multiplied by 2. You move it up by 2. Same thing with cosine. Now, you might be asking yourself, what if we had multiplied by a? I mean by -a. And you just flip it. That's all. It's the same graph, just flipped. Cool. Let's keep carrying. Now, instead of multiplying our cosine or our sine by a value, we want to multiply our x by a value. In this particular case, we're going to multiply x by 2. And to find out what the graph of that looks like, we're going to refer back to the graph of cosine of x. The first thing we're going to want to note is that we know cosine and sine are 2 pi periodic. And we know that 2 times x is going to be equal to 2 pi anytime x is equal to pi. So 2x equal to 2 pi, x is equal to pi, right? All I did is divide the 2 from both sides. Knowing that, we can start looking at this and using this to inform this graph. We know at x equal to pi that the cosine of 2x is going to be 1. Okay. Well, another point we might want to use is going to be pi. And we might want to use it because, well, we know cosine at pi is -1. So now, we want to know when 2x is equal to pi. Well, that's whenever x is equal to pi over 2. Again, all I did was divide the 2 from both sides. Well, I'm going to have to eyeball it on this graph because I don't know the exact point. But I do know something I can use to help me. I know that cosine at pi, or my mistake, at pi over 2, well, I know that's equal to 0. So I can line it up with this intercept here. About here-ish. Speaking of intercepts, those might be some other good points to mark down, right? And we know that this intercept here and this intercept here, this occurs at x equal to pi over 2, and this occurs at x equal to 3 pi over 2. So we can solve for those as well. And 2x is equal to pi over 2, x is equal to pi over 4, which I'm going to have to eyeball it. It's about here, approximately. And when 2x is equal to 3 pi over 2, x is equal to 3 pi over 4. So we know it's going to be between pi over 2 and pi, approximately there. Now, having said all of this, there's one other point we might want to note on. When 2x is equal to 0, well, 0 divided by anything is still 0. So, dividing both sides by 2, we find that x is equal to 0. So this point stays the same. So what we've got, I'm going to erase all of this here really quick. What we've got is cosine of 2x is going to look something like this. something about like that. So you might notice what we've done is we've taken the cosine and we pulled it in. I clean it up a little bit, it becomes more clear. What we've done is we've taken the cosine and we pushed it in, right? We've contracted it down, we've compressed it. This is going to happen anytime you multiply x by a number greater than 1. If, on the other hand, you multiply it by a number between 0 and 1, you're going to stretch it. So, drawing that over here, it's going to look something like that. Compressed, like I said. Cool. Let's move on. All right. So let's wrap this all up into a nice little neat package, right? A set of rules that we can follow and reliably get results from. Rules for graphing. That's what we want, right? So let's say we've got a times cosine of bx plus c, or a times sine of bx plus c. The rules for graphing, pretty straightforward. Whatever a is, you're going to stretch or contract your cosine graph or your sine graph in the y direction by a. That's it. So when are you going to stretch it? You're going to stretch it whenever a is greater than 1. When are you going to contract it? You're going to contract it whenever a is between 0 and 1. For b, depending upon what b is, you're going to stretch or contract in the x-axis. Same thing. Except this time, it's in that x-axis. Cool. The catch with this, I should point out, the catch with this is you stretch it in the x-axis whenever x is between, or whenever b is between 0 and 1, you're going to stretch it in the x-axis. And whenever b is greater than 1, you're going to contract it in the x-axis. So you're going to compress it. So you're probably looking at this thinking, C? We didn't even talk about C. Yeah, C is pretty straightforward. You're just going to move it left or right. So if you're adding a positive value, you're moving it to the left. Just looking at the video and thinking about my left and right. Don't laugh, it's like, what time is it? It's 1:30 in the morning. I've been here all day, I'm exhausted. So, in the case of C, if you're adding a positive value, you're going to take your function and move it to the left. If, on the other hand, you're adding a negative value, you're going to take your function and you're going to move it to the right. Having said that, it would be nice to know when your function starts and ends that first cycle, right? Like we know cosine at 0 is 1, and we know cosine at 2 pi is 1. So it would be nice to know when that first cycle begins and ends based on what B and C are. Well, the first cycle will start whenever bx plus c is equal to 0, and it will end whenever bx plus c is equal to 2 pi. having said all of this, there is one last thing I want to point out before I let y'all go. In the case that we're multiplying by a b, we're multiplying that x value by a b, right? The period, because we're stretching and contracting in the x-axis, the period will no longer be 2 pi. Instead, if we have a b that we're multiplying by that's not 1, right? Then the period is going to change to period will be 2 pi over b. So if we were to say cosine of 2x, like our last example, well, the period became just pi. And we saw that, right? It ended at pi. Having said all of this, there's something else I should note. I've kind of left it out. These functions are continuous for the entire x-axis. So you can put in any x value from negative infinity to infinity. These keep repeating forever in both directions. Same is true for cosine and sine both. Cool, having said that, that's all I've got for y'all. Have a good one, guys.